Welcome to clickmyproject.com. Let's discuss about the product. Our product is an event-based neural network architecture with an asynchronous programmable synaptic memory. In this paper, we have included quad bilateral combination as an enhancement of the paper. That means we are enhancing neural network with bilateral combination. An event-based neural network. Here we present a hybrid analog digital very large scale integration implementation of a spiking neural network with programmable synaptic weights. The synaptic weight values are stored in an asynchronous static random access memory, which is interfaced to a fast current mode event-driven DAC for producing synaptic currents with the appropriate amplitude values. These currents are further integrated by current mode integrator synapses to produce biophysical realistic temporal dynamics. The snaps output currents are then integrated by compact and efficient integrate and fire silicon neuron circuit with spiking neuron frequency adaptation and adjustable refractory period and spike reset voltage settings. The fabricated chip comprises a total of 32 into 32 SRAM cells and 4 x 32 snap circuits and 32 x 1 silicon neurons. It acts as a transceiver receiving asynchronous events in input, performing neural computation with hybrid analog digital circuits on the input spikes and eventually producing digital asynchronous events in output. Input, output and synaptic weights values are transmitted to from the chip using a common communication protocol based on the address event representation, that is called AER. Using this representation, it is possible to interface the device to a workstation or a microcontroller and explore the effect of different types of spike timing dependent plastic tree, that is STDP, learning algorithms for updating the synaptic weights values in the SRAM module. We present experimental results demonstrating the correct operation of all the circuits present on the chip. Spiking neural networks represent a promising computational paradigm for solving complex pattern recognition and sensory processing tasks that are difficult to tackle using standard machine vision and machine learning techniques. Much research has been dedicated to software simulation of spiking neural networks, and a wide range of solutions have been proposed for solving real-world and engineering problems. But these solutions are often implemented as software algorithm running on bulky and power-hungry workstations. In order to apply this computational paradigm to compact, efficient neural processing and sensory motor systems that compute on real-world sensory signals and interact with the environment in real time, it is necessary to develop dedicated hardware implementation of spiking neural networks which are low power and can operate with biological flexible sign of full custom analog digital very large scale integration neuromorphic systems. Here the black diagram shows about the system design of our proposed methodology. So overall design is based on CMOS mechanism. So initially, as usual, for every CMOS design we have to give input as a binary values. So this process is based on memory allocation methodology. Hence the memory unit is designed earlier and the neural network, which is a medium of conducting process. And then in the process mainly we are focusing on checking interconnection, address verification. Then as a medium, we already discussed this acts as a medium. So here the transfer of data occurs and by this neural network with enhanced method the output while we are checking, the performance gives better result than the previous methodologies. We can compare the parameter results and analysis from existing and proposed methodologies. So our proposed results shows we are getting better results than the previous methods. Let's discuss something about the tool. For this CMOS design based methodologies, we have to use CMOS design tool, that is called Tanner EDA tools. Commonly, Tanner EDA tools having lot of subdivisions, that is called SEdit, LEdit, WEdit and such more. There are lot of under devices. So in this we are using SEdit for circuit designing. So and then after we design that SEdit, while simulating, the circuit's design will pass through the T-space that we can understand through the checklist generated through the SPICE code. And finally, while we are simulating, the timing diagrams will appear in WEdit. Hence, commonly for our CMOS based designs, we will use mostly these three edit things. That is, again I will say as SEdit, LEdit, WEdit and T-space. So we can design the circuit based CMOS transistors by using SEdit. Here, before we starting the simulation, we have to select a new cell. Here is the cell menu. Here we have to select the cell menu and we have to select new cell. So there you can select number of cells like cell 0, cell 1 up to cell n you can select. So each cell should contain different CMOS design. And next process is to set up simulation. Here this icon, while you are pressing that will leads you to set up simulation. In the setup simulation you have to set up maximum time duration for the design and nanoseconds based setup methodologies. After designing setup designs, we have to load the library files. So initially for the design of CMOS designs, we need some CMOS components. Those CMOS components will occupy in CMOS libraries. That means CMOS libraries contains components of which required for CMOS design. So here you can see what are the components listed in CMOS library. While you are pressing add, it will leads you a window menu. There you can locate the library file where you have stored. So from the location where you have stored, you can select all components which you can need for your CMOS design. So after design of this cell, you can save the design, and while you are pressing run, it will leads to T-space. So through T-space you can see what are the checklists available in T-space. In T-space, usually the components which you have used are listed in as a component code. That means you can see that as a program wise. That's why that T-space codes are called netlist. You can run either from SEdit or from T-edit. From wherever you are running, the output timing diagrams will show in WEdit. In WEdit you can see the waveforms which we have obtained for corresponding CMOS design. And also you can clarify what are the result parameters, and you can measure all the parameters which you need for the design from the WEdit. Thank you.